Swayam Prabha. Digital India. Educated India.
So, hello everyone. I'm Harish from IIT Madras, but I look an awful lot like Agent Smith now. So, today we'll have two sessions, one on ensemble methods and one on learning theory. I do have an agenda, but that agenda is totally changeable. If you guys have any doubts or any things, I can always pass and I don't have to cover anything. So, my agenda is basically to reach you guys. Okay, that's the most important part. It's not to cover any syllabus because there's not going to be any exams or anything. So it's important that you guys get what's being taught. That's the most important part. Okay, so the first session is on ensemble methods. So we'll just go over an introduction, right? So in practice, right? So in practice, you have many real-world machine learning problems, and there is most often not a very single elegant solution which always works. That is never the case. What generally happens is, say, a problem giver gives a machine learning problem to a diverse team, and each member of the team comes up with a different solution, all of which are equally valid, but they'll be different. So finally, you have to combine. I mean, the best thing, it's usually observed that any single model, any single method does not really do well. But if you combine all the inputs from all the, say, team members and all the possible solutions, you generally get a very good solution. So, in fact, all the state-of-the-art machine learning things that you see are always ensemble methods. So what does ensemble methods mean? It essentially means that you are combining many different, say, classifiers or regressors or anything into one solution. So how do you combine several such solutions, each of which are valid solutions in their own right? You can just use one of them and say that's a valid solution. There's no doubt about that. But it is almost always observed that if you combine all of them together, it works better. So it kind of speaks to the success of democracy. One guy, he's a good unbiased estimate of the entire population. But if you ask more people, you get a better estimate and better understanding of the entire country, right? So it's essentially, ensemble methods are democracy in machine learning. That's how you could process. That's one way to call it. Okay, so that's ensemble methods. Any question that the definition is how do you combine multiple separate models, either be classification or regression or anything? How do you combine that into one single model? So that's ensemble methods. Okay. So if you have any questions, feel free to stop me. So this is just a definition. Okay. So just go with an example first. So there was this Netflix challenge. How many of you have heard of this Netflix challenge? Okay, a sizable number of you. So Netflix challenge was perhaps the first huge application and added huge glamour to actually machine learning, because it was a huge data set then. I mean, by today's standards, it's not really huge, but when it came out, it was humongous. It's 100 million star ratings of 500,000 users to about 18,000 movies. It's a humongous data set. And what Netflix wanted out of it was for individual teams to build a star prediction solution. So essentially, you have this data set, and then finally, what Netflix wanted you to do was, it would give you a new user, or maybe a user in the same set, or a movie in the same set, and it would ask, well, you know how, say, these 500,000 users have predicted these 18,000, have some subset of 18,000 movies. Now, how would this user rate this movie? So you have not seen that particular data point, but still you know enough of it. For example, you know that, say, what's your name? Mithilesh. What's your name? What's your name? Sunena. Okay, so for example, say, you find that, say, Mithilesh likes Lord of the Rings and Sunena also likes Lord of the Rings. And say, Sunena also likes, say, Harry Potter, but Mithilesh has not rated Harry Potter. So now you want to ask, okay, how does Mithilesh rate Harry Potter? So now you don't really know. I mean, your data set does not really have the data. But given that you know both Mithilesh and Sunena liked Lord of the Rings, you can kind of guess that, well, they are likely similar. And given that Sunena liked Harry Potter, well, maybe Mithilesh also liked Harry Potter. So that's the standard approach in which you would learn. So this is a very relevant problem. It's called collaborative filtering, but there are many approaches to solve this problem. And this you can, off the top of your head, you can think of many solutions, and that's what really happened. So, and what was the glamour part to this? The grand prize was $1 million for a team which beat the Netflix standard by 10%. So Netflix already had a prediction scheme, which it was using for recommending movies to users, but it wanted it to do better. So it asked people to come up with a new rating scheme so that it can recommend better movies. So that was the goal, and it gave a grand prize of $1 million for any team that beat the Netflix benchmark that they were using by 10%. That was the goal. And this was, this became famous for a different reason afterward, but the original reason it became famous was simply the scale of the problem and the scale of the prize money. And so, okay, that's fine. That's enough background about the Netflix challenge. So what was the winning solution? So the winning solution, the winning team was called Belcor's Pragmatic Chaos, which itself was a merger of at least 4 teams. I think it was first Bell Labs team, and then Yehuda Koren's Yahoo team, and then there was a Pragmatic Ensemble team, and then there is a Chaos team. So all of them merged together. So everyone thought that, okay, we're all beating the thing by 5%. Maybe if we all join together, we can beat by 10%. So that itself is an idea of how ensemble methods come into play. Well, different teams come, they have different set of models, and so finally, the winning solution actually had 107 separate prediction models. Each of them were valid. Each of them actually individually beat the Netflix model. But by combining all the 107, so each one of them was a valid model. You could have just used one of them and said, yeah, that's the model, you could have said that. There's nothing wrong with that. But by combining all the 107 separate models, they beat the Netflix, the algorithm the Netflix was using, which was called Cine Match, I think. So it beat that by 10% by combining such models. So the methods were all over the place. There are different kinds of approaches. They use factor models, like how they compress users and movies into, say, small dimensional vectors, and use hidden factors to represent it. They use regression methods. They use neighborhood models. So all the 107 models, each of them used a different approach. All of them are equally valid under different assumptions. But combining them gave a much better answer. Okay. So in fact, there are other teams which also came close, and almost all of them used ensemble methods. So when I say ensemble methods, they combine a different model, so that means that it's an ensemble method by definition. So how do you combine that? That's the first question you should ask. Okay, so I can train separate model using different assumptions. How do you combine that? And that is essentially the core of ensemble methods. Okay. So yeah. So there are 2 paradigms of ensemble methods. One is the parallel ensembles, which is what I've been exposing now, expostulating now. So you have several models, each of which were trained without the knowledge of other models. Say, for example, if you have, say, Belcor's team, and then you have Pragmatic team, and then the Chaos team. Each team trained models without the knowledge of what the other team trained. They did not really know what the other team was training. But still, you have trained all these models, and then you combine them together. So when you train individual models in your set without the awareness that there are other models out there, that's basically parallel ensembles. You can see why it's parallel, right? You can train all of them in parallel. You can have 107 computers computing those 107 models separately. There is no dependence on, say, model 1 with model 2 and model 3 with model 106. They are all separate. So they can be run in parallel. That's a parallel ensemble. And so this allows naive parallelization. And then there is the other type of ensemble methods, which is the sequential ensembles. So you can clearly see what the difference is. So every time you build a new model, you are going to use all the previous. So you are going to build models now one by one, not just 107, all 107 thing immediately. 107 was just some number I'm telling you, but you can build however many models you want. In sequential ensembles, you don't build all of them simultaneously. You build the first one, and then you build the second one, and then you build the third one. So when you build the second one, you use the first model that you've already built. And when you build the third one, you use the first and the second. So it's a sequential. So you can't parallelize this. So you have to do it sequentially. So the prototypical examples of parallel ensembles are bagging, and the prototypical example of sequential ensembles are boosting. So I will try to, there are many other examples also, but these are the prototypical examples that you will see, and I'll try to give an idea of both these methods. It's bagging and boosting. That's basically the agenda for today, to introduce you to both bagging and boosting. Okay. So any questions so far? So now we'll focus on the parallel ensembles, just bagging first, okay? So what is the intuition for bagging? So imagine a situation where you have individual learners, and they are all high capacity. And what do I mean by that? they generally overfit. I'm sure Arun has taught regularization and overfitting to you all. So if you have only say 10 data points and you fit a 7th degree polynomial to that, you are going to get a very close to zero training error, but that does not mean anything. You are generally overfitting it. So these kind of high capacity, so this is high capacity learner. So if you have high capacity learners, they generally overfit. So the one option, no, but you don't really care about training error. What you really care about is basically the testing error, or how your classifier or your regressor performs outside your training set. That's what you really care about. And how do you take care of that? So one way to do it is, as Arun might have told you, you use regularization. So you minimize the complexity, so you constrain the complexity of your model somehow and do that. So that's one way to do it. But for several learners, it's not always clear how you do it. And it might not really be the best approach. So, and that's where bagging comes into picture. So bagging it does not really you don't know how to regularize it. That's fine. So it's just a black box. Somehow you plug in, you have a learning algorithm which you don't want to touch. It's working, and if you touch it, you are afraid it will break. But what you are only willing to use it as a black box. So you want to just regularize now. So you mean if you use standard regularization techniques, you have to change the penalty function or add extra constraints and so on, which will really break the black box. You can't really. So that's where bagging comes. You want to regularize without breaking the black box. And that's where bagging comes in. The bagging is a very, very simple idea. And what it does is it sends to the black box different subsets of your data. So say, for example, if you have, say, 100 data points, training data points, and you take, you say, sample 50 points from these 100, and you send to your black box. You get one classifier out. And then you sample another 50 points from the same data set. It might overlap, it might not overlap, it's fine. So that means that every time you sample, you are going to get a different a different classifier or a different regressor. And that way, you are going to have multiple classifiers or multiple regressors. That's the idea. So, and you can somehow combine them. And you can see this is trivially parallel, right? I mean, you can, if you have the training set, say the 100 data points is fixed, that means that you can keep on doing that, right? I mean, you can have 100 computers selecting 100 subsets of the 100 samples, and then you can learn the 100 models in parallel. So that's something which you can do. So this is a naive parallelization is possible, and that's bagging at its essence, okay? So, and what is the key insight that allows it to work? The key insight that allows it to work is that high capacity learners are going to give very distinct models if you give different subsets of the data. So if you give, say, maybe samples 1 to 60 of your data set, it's going to give one classifier. And if you are going to give samples 40 to 100 of your training set to the model, it's going to give a very different classifier. So there is a diversity in here. So when that happens only for high capacity learners. If your learner is very low capacity, say for example, your learner is, say, your classifier, there is the trivial learner. It always predicts positive or always predicts negative. So these are the only two things that you have. In this case, there is not a high capacity thing. It's a very, very low capacity thing, and you are just going to take majority vote and predict. That's what you're going to do. It's a very low capacity thing, and in this case, it is not going to vary very much. So if you, say, select the first 60 or the last 60, it is not going to matter much. But high capacity learners are very, very sensitive to these training. So I'll illustrate it with an example. So this is one example, okay? So this is synthetic data. So you have data here, which is actually, you have two Gaussians generating data from positive generated from this Gaussian and negative data generated from, say, this Gaussian. So they are centered at, you have negative data centered at -1 and positive data centered at +1. Okay. So that's the Gaussian, you're generating Gaussian data. And now you use a very high capacity learner. So what learner I'm using here? So I'm using basically support vector methods with the support vector classifier with a Gaussian kernel. But you don't need to worry about that. You just need to understand that it's a high capacity learner. So I used one subset for training this model, this classifier, and another subset for training this classifier. You can see that they are both more or less, you know what the right answer is. The right answer is clearly you threshold at 0. Anything above 0 is positive, anything below 0 is negative. That's the right answer. You know the right answer because you generated the data. There is no real doubt about that. You want your learning algorithm to get to that. That's what you want to get to. But say you train your first model using half the data and your second model with another half of the data. I mean, it's not another half. There could be intersections. For example, you randomly toss a coin for every sample, and you decide to include it or not. So that's how you get your first half, and then you get the other half by doing that. So there could be intersections. And when you do that, because it's a high capacity learner, it overfits it. So it kind of sees one positive point here and one negative point here, and it's trying to get it 100% accuracy when it's actually not possible. So even the best classifier here cannot get 100% accuracy because there is an overlap here. I mean, any negative point that goes above 0, you cannot do anything about it, and any positive point that goes below 0, you can't do anything about it. So there is no, I mean, even the best classifier is going to make mistakes. But because it's a high capacity learner, it is trying to make 0 mistakes, and it is trying to do too much, and it overfits the thing. And because of that, you can see that the classifiers learned are very, very different. So you have one classifier here, and both are individually okay. They look more or less the lower part of the XY plane is negative, and the upper part is positive. That general trend is correct. But the boundary, near the boundary, you can see it's very different. So this happens because you are using a high capacity learner, and just by training the high capacity learner on different subsets, you're getting different things. Okay, so that's one idea. Okay, now I can get multiple such things. Then how do finally, I don't really care about these things, right? I want to get one single answer out of it. So I'll say, for example, I might ask, so what is the result for this point? Or what is the result for this point? So is this point positive or not? So is this point positive? Is this point positive? Is this point positive? So these are the kind of questions I will ask finally. And I don't want multiple answers, I want a single answer. How would you go about doing that? Any suggestions? So you have trained, yeah?
You can assign weights to different classifiers.
Okay.
Finally, you can take the weighted average.
Yes. Yeah. So what's the trivial weight that you can assign? Okay, so assume all classifiers are trained using the same number of training points.
The accuracy.
Accuracy of what? On what? So accuracy of, say, this is classifier 1, this is classifier 2, and classifier 1 is trained on dataset 1, this is trained on dataset 2. So you have both D1 is a subset of D, and D2 is also a subset of D. That's fine. So you can use accuracy. So that's kind of going a little bit ahead, but the trivial thing to do is to give equal weights to everything. So trivial, that's you just give, say, if you train 100 classifiers, you give equal weights to everything, and when you get a new instance, you ask all your 100 individual models, what do they say? So, and you find that out of the 100 models, say 70 of them say positive and 30 of them say negative. Then you say, okay, because a majority of them say positive for this point, I'm going to say positive. So that is the simplest thing that you could do, and that is bagging. That's it. Okay. So you've already gotten to. So it's a very, very simple method, but you would be very, very surprised by how powerful this is. It's yeah, and that's basically it. So any questions on this? We'll go do a little bit of theory, but don't worry too much. If you get this part of it, you are fine. So the theory is there to just show that it is not simply just averaging. I mean, it's not as simple as averaging. I mean, the algorithm is as simple as averaging. Generally, this is how you would find most machine learning algorithms. The algorithms are mostly very, very simple. But the analysis to show that it is a reasonable thing is very, very complicated. So you can understand it at different levels. You can get the algorithm, which is what, say, for example, say a data scientist at a company would do. So he does not need to know why it is going to work, when it is going to work. He's just going to apply methods. But if you're going to become a researcher or want to develop new algorithms, then that means that you need to understand why and when it is going to work. For example, here, right? So I said that it will work only if your learners are high capacity. And so that's something I said. But how is that quantified? I mean, what do I mean by high capacity? What do I mean by that? So these are the kind of questions you should ask. Say when you are trying to develop new algorithms. So you can understand it at the algorithmic level for now. That's not a problem. But you should understand that there is a deeper level that you need to know when and why it works. So that's the next level. Yeah. So any questions up of the algorithm? Yeah. Yes. Mm-hmm. Yeah. you just set the answer, average. So for example, say learner 1 predicts 2.3, learner say regressor 2 predicts 5.7, and so on. You just take the average and you can do it. So that's a standard way. There are other more complicated ways, but this is basically the simplest way to do it, and it's the most popular way to do it, actually. So you will see both bagging classifiers and bagging. Bagging classifier generally means majority voting. Bagging regressor means generally averaging. That's the general idea. So, any other questions? Yeah, then I'll just move to a little bit of theory. Okay, so let's take this, right? So you have the sample. So you have x1, y1, x2, y2, dot. You have, say, xn, yn. You have these samples, okay? And this is your entire data set. So how would you go about your first bag? Why is it called bagging? Because you construct several bags. And in each bag, you choose, say, a standard thing to do is to choose half the sample. So if you have n, you choose n by 2 samples. But there are this constant, you will find it different. Sometimes people say you need to choose 60% of the samples, you need to choose 70%. So that number generally is subject to variation, but it's a number that's generally between 30% to 70%. So we can choose 50%. I think that's a reasonable, easy number to choose. So one thing that you will find with bagging is sometimes people say, we sample with replacement, and sometimes they say we sample without replacement. So are you aware what that means? Sampling with replacement, without replacement? Yes. So that means that you are sampling without replacement. If you're sampling with replacement, you can sample the same point multiple times. So that also happens. So generally, bagging is done with sampling with replacement. So it's possible that x1, y1 can come 2 times. It is possible that it can happen. But generally, those examples are going to be pretty rare because you have, say, 100 samples and you're sampling 50 out of them. The possibility that you're going to get the same sample twice is quite small, but it is possible. So that's the general way in which bagging is done. But you can do sampling without replacement also. It's also valid. But people find that sampling with replacement works better. So that's the general. So you could have this, and maybe you have, say, x3, y3. You say x7, y7, and say you xn minus 1, yn minus 1. So this is, you would get one bag, and you could get another bag, which may be x2, y2, x4, y4, similarly, and so on. So this is bag 1. This is bag 2, bag 3. So on, you would have multiple such bags, which is from your original big bag. And then you would just give each of these. And one terminology that you would use this, say, call this as S. And one terminology that you would see often for these bags is basically bootstrap samples. So that's a terminology you would see, but don't worry too much. I mean, when you see the statistics terminology, it comes from generally these bootstrap, jackknife, these kind of statistics techniques. They are older than machine learning. So they are comes in statistics. It's about 100 years old. So machine learning borrows heavily from statistics, and bootstrapping it's a terminology used in statistics. But that's what it is called. So it calls a BS, say BS1, BS2, BS3. So you have all your BS I's. They're all subset of your S. So S is your set of all samples, and it's kind of it's not exactly a subset. It's a multi-set in the sense that you can have things that are repeating, right? So I said you are sampling with replacement. That means that your B bootstrap samples are not exactly sets, but rather multi-sets. A same set can repeat. So that's fine. You can always add maybe your index also into the thing, so that if you add an index there, that means that you're always going to be unique. So your set terminology issues will not bother you. But if you are concerned about that, you can call it a multi-set if you want. Okay. So that's the idea. So now you have these bootstrap samples, and say you have a black box learner. You don't want to, as I said, right? You have a black box learner which you don't want to touch. So you have a black box learner which you don't want to touch. So what that does is it just takes in your BS and it gives you HBS. Okay, so that's going to be your classifier. So it's a black box which takes in your bootstrap sample BS, and it gives you a classifier which is R regressor. I'm going to stick to classifier throughout the talk, but in almost all cases you can also extend to regression. Okay, so you don't want to touch this black box. You just know that these black boxes are reasonably good. They are going to give you not horrible classifiers. They're going to give you reasonably good classifiers, but the objective of this is to combine good classifiers and make them better classifiers. That's the idea. So you get your HBS. And finally, what you are going to return is your capital H, which is the bagged classifier, H of X. So for some instance, okay, fine, I just assume here. So H of X is simply the expected value of HBS of X. So now this expectation is over the random draws of your sample, bootstrapped sample. So if you have say 20 bags, that means that it's over 20. You are drawing 20 subsets of your sample. That means that that's an expectation over that. Okay. So what this said, don't worry we'll just get to what this is trying to show. What this is trying to show is, in terms of least squared error, the bagging classifier or regressor does no worse than any of the individual things. The first thing, even if you know any medical philosophy, the first thing is not to treat people. It's first to do no harm. That's the first philosophy. So that's the same thing. You already have individually good things. By combining them, you should first ensure that you are not doing any harm. And then you can show when you're doing better. So that's what it will show. So irrespective of what the condition is, you are not going to do any harm. That's what we will show. And under certain conditions, you can do better. So now, under no assumptions now. There are no unstable learners, there are no assumption I'm making. Sorry, no unstable learners, no high capacity learners, no such assumption I'm making. But I'll still be able to show that the bagged classifier or the bagged regressor is no worse than an average thing that you get from your individual things. That's what I'm going to show. So say eta of X is the ideal classifier that you want. So eta of X is, generally this is a notion that you will see, terminology that you will see often. Eta indicates the expected value of Y given X. But don't need to worry about that. So you just take eta of X is the best classifier that you can possibly get, or the best regressor that you can possibly get. That's eta of X. And your H of X is the thing that you are actually predicting, right? So eta of X minus H of X squared, you want that to be actually less. So that's your least squared error, and you want that to be less. And by definition of your H of X, you have H of X is simply EBS of HBS of X. That means that you can just write it down this way. Okay. Right. So are you all aware with basic probability, right? So its variance of any random variable is always greater than or equal to 0. That means that of any random variable, you have expected value of X squared is always greater than or equal to expected value of X, the whole squared, right? So that's the one thing I'm going to use. So that means that you have expected value of X, the whole squared, right? You can call this entire thing as your X, your random variable X. Okay, that's expected value of X, the whole squared. That is less than or equal to expected value of X, EX squared. That means that I can bring in the squared inside the expectation, so that I can do that. Okay. And now this is for a single point X in your instance. Okay. Now I can take the weight over all possible X's, and that is going to be my mean squared error of my bagged. The left-hand side is simply going to be my mean squared error of the bagged regressor or classifier H. And the right-hand side is going to be the expected value of the mean squared error of the individual things. HBS was the individual learner that you had. And this is saying that the mean squared error of the bagged regressor or classifier is always going to be less than or equal to the average mean squared error of the individual things. So by doing bagging, you are not, this is a proof. I have made no assumptions. The only assumption, there is no real assumption at all here. Okay. So by doing bagging, I'm not hurting. So that's the first thing to note here. Okay. So that means this is the take-home message. The mean squared error of the bagged model is no worse than the average mean squared error of the individual models. So now we have met the first maximum of medicine, that we are not doing any harm. Okay, that's good. But we are not here. If this is what we wanted, we might just as well have taken just one of the bootstrapped models, right? So individual models, and that would have been good. But here's the thing. This is a less than or equal to. When is this less than or equal to very, very less. So I mean, we don't want the equal to side. We want to see when is this less than case true. That's what we want to see. And the only place where we have used that is basically the variance of this. So that means that when is mean squared error of your backed regressor or classifier very, very less than the average mean squared error of your individual things. So you can just do that, and essentially that will turn out to be saying that your variance of each individual say regressor or classifier is large. So what is the random variable here? The random variable is simply the bootstrapped sample. So that means that when I sample different subsets of my full training data, my HBS should be all over the place. That's kind of saying that you want diversity. So for a given X, if I sample different subsets of training data, my learner should give different answers. So when is the variance high? The variance is highest when it's, for example, if it's a regression problem, it should be, say, it's either a uniform distribution or a Gaussian distribution. So under different conditions, you'll get that. If it's just a classifier kind of thing, it's just a classifier, that means that you want 50-50. I mean, that's the best case. That's what maximizes the variance of your HBS. Okay. So that's what you want. And that's where the essential things comes from. So bagging works successfully when you have unstable learners. This is called an unstable learner. So essentially, you just change the training set by a little bit. Instead of training on the first 60 samples, you train on the last 60 samples, and you get a completely different classifier or regressor. When that happens, your variance is going to be very high, and that is the case when bagging is going to be successful. That means that your mean squared error of your bagged regressor or classifier is going to be very, very less when compared to the individual mean squared errors. So that's the idea. So is this clear? I mean, just get the two main funda. That's basically mean squared error of bagged model does not hurt, and when it helps is because when there is huge diversity in your trained models. That's the idea. Is that clear?